Hello everyone. My paper is Safety Boundary in Virtual Reality, an approach based on user motion analysis and prediction. As virtual reality develops rapidly, it gradually enters the public's field of vision and gains popularity. The application scenario includes education, medical care, entertainment, and so on. With the improvement of hardware devices and software upgrades, users can experience more realistic virtual scenes. However, while having a deeper sense of immersion, users are likely to lose the perception of the surrounding physical environment, which may lead to colliding with objects around them, causing damage to the equipment and even users' body. The term safety boundary firstly proposed by some VR hardware companies. The system requires users to delimit a boundary in the area without any obstacles as a safety area before using VR equipment, called safety boundary. However, the fatal limitation of this method is that the boundary is static, and the alert will be triggered only when the user is close enough to it, and the user will not be able to change the movement state in time. Also, the existing safety boundary cannot provide suitable warning time for different users, and the user's activity range will be limited if the boundary is set too small. Therefore, it is necessary to optimize the traditional safety boundary into a dynamic boundary that can provide timely warning for different users. Research shows that when users operate devices in VR scenes, their actions have obvious personal characteristics and contain a lot of important information. We speculate that certain information features can be obtained from motion information. According to the features, the system can predict the next movement of the current user in real time to adjust a safety boundary range and give an early warning. In order to improve the safety boundary, we consulted a large number of relevant literature. The related research could be divided into following two groups: motion features analysis in virtual reality and user safety in virtual reality environment. Based on the excellent viewpoints in these papers, we propose our methods. Our work mainly involves 4 contributions. We will introduce them in the following sections. Before the experiment, we made a series of preparations. According to the research, the main users of VR are teenagers. Therefore, this paper mainly recruits volunteers for college students and teachers. The hardware configuration is based on HTC Vive and Pico Neo 3. Each set of devices includes one handset and 2 controllers, and 2 trackers are attached to obtain the motion data of the user's legs. Next, we will introduce the selection of VR scenes. In the process of VR scenario selection, we believe that the ideal scenario should meet the following requirements. It should be easy to get started, and a certain difficulty needs to be set. The scenario should guide users to make typical action. The selected scenario needs to be modifiable, highly expandable, and support secondary development. There must be a certain degree of freedom in the actions. Based on the above considerations, we chose the open source project OpenSaver. After entering the OpenSaver, players can score points by cutting up the rhythm blocks that fly at them from different angles to the beat of the music. And we summarize and define 3 main types of VR motion events: slashing in front, slashing beside, and slashing backhand. We set the user's shoulder and head as a reference system plane. Draw a 90-degree axis according to the right shoulder. When the block flies to the user, if it locates on the slide near the head at the dividing line, it will be counted as event A. Otherwise, it is counted as event B. Event C is a reverse cutting action, like we use the left hand to grasp the object on the right side. It is worth mentioning that we only focus on user's motion under the horizontal plane. Therefore, if a user makes the right cutting action and is classified as event A, it means that the user may have made one of the right horizontals, right up and right down cuts. Volunteers first provided informed consent and then completed the questionnaires. The questionnaires contains the basic characteristics of users, such as gender, age, and VR experience. User-based characteristics feature is shown in the table. After completing the questionnaire and training phase, volunteers were instructed to begin the experiment for collecting motion data. We used a sim music track and set a medium difficulty. Each volunteer played 3 times. To obtain the motion data, we wrote a C# script and applied it to the camera of the headset. The system obtained the 3-dimensional position information of the headset and controllers. We aim to obtain the horizontal range distance of the left and right handles relative to the headset. According to the 3-dimensional coordinate system, the range of motion range of each frame in the text is shown in the formula. After obtaining the user's motion range data, we carry out the following steps. We decided to segment the events of the game according to the occurrence of the reason block. We divided the period into a series of VR events. We took each event as a unit to find out the max motion range distance, and then we took this value as the max motion range distance of the corresponding event. Now we need to analyze and cluster the VR motion ranges of these 3 motions respectively, to divide the range into different levels. We determined the optimal number of classes for each motion range cluster and set the key value as 4. In our research, what we need is a boundary of the category, so we convert the centroid location into the boundary location. Finally, we concatenate the basic feature data of the user with the magnetic categories of the motion events to obtain the constructed relation dataset. To study the correlation between user features, we conducted a spearmint correlation analysis. Then a two-tail test is used. We can observe that the user's age and proficiency in game have a positive correlation with the VR experience and the user's range of motion, and the impact is more significant. The user's weight has a negative correlation with the range of motion. The height of the user is negatively correlated with the range of motion. Then we use sport vector machines to train and predict the dataset. The accuracy of the training set and test set trained by the NUSVC model is the highest among all models, and the performance of the SVC model using the radial basis kernel function is also better, indicating that the RBF kernel function can perform a high-dimensional mapping of sport vector machines. Supported by the above results, the runtime data will be transmitted to the model to predict the 3 VR motion events, and the corresponding action range categories will be output respectively, and the system will dynamically adjust the safety boundary. As shown in Figure 6, the distance between the VR helmet and the static safety boundary should be greater than or equal to the distance between the dynamic distance and the static safety distance. To distinguish between dynamic and static safety boundaries during actual project deployment, we use orange as a color for dynamic safety boundaries and blue as a color for static safety boundaries. Figure 7 shows the static and dynamic VR safety boundary in actual deployment. That's all. Thanks for listening.